One of the ways to solve an equation using matrices is the matrix inversion method. By taking the same set of equations as used in the last lesson, you can easily recall that here the variables are x and y. The numbers attached to them are coefficients and these are the constants on the right side. We will transform these equations into three matrices: a matrix of coefficients, a matrix of variables, and a matrix of constants. So, put the coefficients in the coefficient matrix, the leftmost one. The first column is for the coefficients of x. So, A and C come here. The second column is for the coefficients of y. So, place B and D here. In the variable matrix, the one in the middle, we have x and y. Finally, in the constant matrix, we put m and n. Guess what? These matrices exactly represent these equations. Don't believe me? Try multiplying these two and you will get the equations again. So far, we have one matrix for each: coefficients, variables, and constants. I am labeling them as A, X, and B. Ax equals to B. We discussed earlier that solving an equation means finding the value of variables. Here, the matrix related to the variables is x. And to isolate it, I cannot simply take A here. X equals B upon A. Something like this can't be done in matrices. Then what? We can follow another appropriate procedure. Watch. I'm multiplying the inverse of A on both sides. Why? Because we know this from our previous lessons that A into its inverse is equal to unit matrix I, and I multiplied by any matrix gives that same matrix again. AI equals A. Thus, we have arrived at a formula for x, or the unknowns, where x is the matrix of variables, A is the matrix of coefficients, and B is the matrix of constants. To use the formula, you only need to find one inverse and perform one multiplication. This inverse is what gives this method the name matrix inversion method. Well, let's start solving. The inverse requires the determinant and the adjoint. The determinant can be found by cross multiplying these two minus the product of these two. And the adjoint is obtained by interchanging the diagonal entries and changing the signs of the other two entries. Put them in the formula to obtain the inverse of A. Now, this is to be multiplied with B. Their orders are 2 by 2 and 2 by 1 respectively. The second and third number are equal. Thus, multiplication is possible. These two numbers show that the resultant matrix's order will be 2 by 1. Therefore, you need to fill these two positions. Now, start multiplying by taking the first row of the inverse of A and multiply it by the first column of B. So, here comes D into M minus B into N. The same goes for the second row, first column, to fill this position. And then, you divide each entry by the determinant. I know this looks complex, but the concern here isn't the pattern of alphabets. You should focus on the procedure being followed. That is, if you have equations to solve, you will convert them into matrices first, then find the inverse of the coefficient matrix, and finally multiply it with the matrix of constants. Simple. In the end, you will get this situation. A 2 by 1 matrix is equal to another 2 by 1 matrix. The similar order and equal sign show that the two matrices are equal. Hence, we can compare the corresponding elements. Therefore, x is equal to this and y is equal to this. That's really it, guys. You have solved a system of equations by using the matrix inversion method. We will solve a problem using this method in the next lesson. That will make things even clearer. See you!